streaming live on YouTube and everywhere else. Yesterday I have figured out why I wasn't able to communicate with the distance sensors on this board. This board has 4 time-of-flight laser distance sensors, and the reason I put them on this board is because I want to be able to kind of like read the position or read the orientation of this board with respect to the surface, because this is an optical sensor which needs to know the distance to the surface. But it would also be nice to know if it's tilting a little bit, kind of to know the orientation of this board relative to the surface. So the IMU cannot tell me that. IMU can only tell me the absolute orientation of this board. So I need some way of sensing against the surface. And for that, I need at least 3 sensors. So having 2 sensors is kind of like, it's not enough. I could still test reading them in parallel, see if there's any interference between the sensors, see if I can get readings, like just check how fast I can get the readings, which is all interesting information, but I still would like to kind of make the most of these boards, even though I have some issues with them, and to get all of them working, so that I can at least have 3 of them, but 4 is much better, because then I can just I can fit a plane to all 4 readings, and then I can calculate the orientation, so I get like 1 reading as a redundancy, just to accommodate for any kind of variation in the other readings, and get sort of the average fit for this plane. In order to get them working, I think it's actually good that I had the voltage conversion, even though I ended up not using the voltage conversion from 3.3 volts to 2.8 volts, because the sensors are 2.8 volts, and the rest of the board is driven by 3.3 volts. But the sensors are actually specified up to 3.6 volts. But the datasheet says that the power supply should be 2.8 volts for the sensors. So it seems to work fine, that they actually interact with the 3.3 volts I2c bus. And the fact that I had the voltage conversion chips here actually means that I can disconnect the other 2 chips from the I2c bus, which currently doesn't work at all, because the PB11 pin, I think it was PB11, is actually not available on this stm32F413, and instead, in the same place where PB11 was supposed to be, there is the VCAP output, so there is no I2C functionality on that pin, and therefore I cannot use I2C2 in this configuration. I would have to reconfigure it to some other GPIO, which I cannot do because that would involve redesigning the board. So what I'll do instead is just hotwire them all to the same I2C bus. And in order to do that, all I need is essentially just to wire the SDA and SCL lines between the I2C buses. So I'm going to have 2 jump wires going across the board and connecting the other 2 sensors to the I2C1 instead. And that should let me read all of the sensors. I won't be able to... I may still be able to take readings in parallel, but I wouldn't have true parallel operation of the sensors. Like, I wouldn't be able to actually write the I2C commands in parallel. But that's okay. I think for this test, that's going to be sufficient to do all of the testing with this board before actually fixing all the faults and actually making this into a production-ready board. So I'm gonna start with actually wiring this up. I'm gonna wire 2 boards, so I at least have 2 boards that are fully functional, and the other 2 boards I can keep for now and maybe use some of the components. If something doesn't work on these boards, I can just use the others as donor boards. So I have a board here which I'm gonna start with. It's already connected to the serial port and the ST-Link programmer. So I can just, all I have to do is just jump wire the I2C bus. So what I need to do now is just to find some cables. I need some very thin wires. So I think I have some thin wires here somewhere. I have one of these connector wires which are quite thin, so I can massacre one of these connectors and just use the isolated wire so that I don't short anything along the way. And I will need a length of something like let's check the PCB layout first, so that we get an accurate measurement of the length. So I have the PCB layout here, and I have the functioning I2c. The one that's working is the one that's here. So the one that is not working is the one that's here. So this one will need to connect to the other I2c bus. So it's going to go from here, from the 2. From the 2.5 volt SDA. It's actually supposed to be 2.8 volts. This is just an error in the labeling, which I didn't discover either because I didn't actually review this board, which is something I regret a lot. Because I had to do a lot of hacking on this board. I had to do a lot of debugging on this board, which I could have easily avoided if I just checked every single label, every single pin between every single component on this board. But I didn't do that, so that's my fault. So I will go from here, and then I will connect this up here. Let's see if we can get some measurement here. And this will go, it doesn't really matter which set of pins this connects to, just as long as it's actually, let's see. Can I get some decent zoom so I can at least get an accurate, so I can at least see the text on the pins. Let's see. That's I2c. Yeah, so this is I2c pins. And let's see if we can just drag the measurement here. So this will go from here, and then it can go underneath there. And the straight line is like, let's see, what is this? Is it R? Is R the straight line? Sounds reasonable. Like something like maybe 8 centimeters. That's pretty much what I need. 8 centimeters of wire. So let's do that. I'll actually try to lay it out around the switch, and I don't want to have the wires too long because I don't want any wires hanging from the surface of the board. I'm gonna glue these wires later. I'm gonna do like Samsung. I'm gonna use glue to assemble my products, and then the wires should actually be stuck to the board and without any parts that stick out. So let's see. So this will be these two lines. I'll just place this here. I should do pretty well if I make the wires this long. So actually something like this. And then just take off the isolation from the wire. And other one. And so I'm just checking because this is actually mirrored when I turn the board around. I could like flip the board, but it doesn't really matter. I can see where I should connect the wires. So this will go there, SDA, and is the SDA in the same place here? So SDA is close to the, yeah. Okay, cool. So let's do this. And wait a minute. What happened here? Oh, okay, yeah, good. So I just realized that I looked at my power supply and I realized it was consuming 0 amps. So I wondered, why does it consume 0 amps? But I disconnected the power cable connected to another board. I don't need the power cable right now, but I just want to make sure that it's connected. Let's solder the wires. So I'm gonna use SDA, white wire for SDA. Doesn't really matter what color it is. Just as long as it connects to the other SDA line. And I'm gonna get some air flowing here. Okay. I like this flux very much. This is sold like Amtech flux. I don't think it's Amtech flux. I don't think it's a real Amtech flux. But there's something about this flux that makes it very, very easy to solder with. It's more, it's kind of more dirty than the other flux that I have. When it burns, it gets yellow, but the solder flows much better with this flux. Much better. And I don't get the solder joints that just let go because I didn't like. I don't have to put in a lot of effort to get the solder joints perfect with this flux. And this will go around here, and then it will come out. Let's see. So this one should go to the edge, and to the connection that is at the edge, all the way in the corner. Oops. So I'm soldering it to the jump wires that are already in place, and I must make sure that I don't overheat the jump wires that are already connecting across this voltage conversion chip, which used to be there. I removed the voltage conversion chip, so it's not there anymore, but the idea was to place it there. So my previous hack is to just hotwire the I2c connection between the 3.3 volt side and the 2.5 volt side, or 2.8 volt side, if we're going to be exact, according to the actual board voltage levels. So now I got this
wire also in place, and I got a little bit too much solder, so I'm going to make sure that there is no solder bridge. Okay, and this looks extremely horrible. It's looking like a true Frankenstein board. Absolutely horrible, absolutely disgusting, covered in flux, and yeah. Let's see, I'm gonna bring up the microscope here. But the main thing is to actually make it work. To actually make the software communicate with the sensors, and then do all kinds of experiments with them. Let's see. Is my microscope turned off? Yes. So one of the things about this Chinese microscopes is that the screen, the backlight dies very quickly in them. So after a few weeks of usage, this one lost its backlight. So it's supposed to be a screen here where you can actually see what you're working on, but the backlight died. I can only see the image if I kind of put it under the light. So I use it as a USB microscope instead. I mean, that works fine. It hasn't broken yet. I will just bring up the image on my screen, which is actually better when streaming. Let's see, yeah. This is what the joint looks like on one side. Let's see, so there is no... Let's make sure there is no connection between the leads. This is my gigantic, thick wire, and this is the connections that are connected to the jump wire. And then the jump wire goes all the way to the other side of the board and connects to the pins of this I2c voltage conversion chip. And let's see, was there anything else I was going to do here? Okay, so the next step here is to solder on the two sensors which I removed when I was debugging the board. So these two sensors are of this model, what's called VL6180. And actually I need to bring up the datasheet of this sensor again. Let's see. Proximity and ambient light sensing. This is the sensor I'm going to be soldering. It's a tiny sensor that melts past 260 degrees. So I have to keep the solder, the hot air at maximum 260 degrees. I cannot go beyond that because then the sensor melts. But I'm going to make sure that I have enough flux on this on the pads where the sensor is going to go, so I get some decent solder flow there. And then I'm going to preheat this a little bit so I get so that the flux melts. And with this flux, I actually apply it with like a Q-tip thing, so it's a bit messy, but it works. And it's actually a very practical way to apply this flux, because I usually need like at least quite a bit of flux so that it starts flowing around the area where I'm going to be soldering. And then I'm going to place the sensors, and the sensors are let's see. You will not actually see anything until I've actually placed the sensors and soldered them. It would have been perfect if I had the microscope showing my soldering in real time, but I need to somehow fix the microscope above here. I do have a little stand for the microscope, but I find that it's a bit too small, so when I work on the larger boards, I cannot actually get the board underneath the microscope, because the stand actually goes to the table and underneath the plate which I'm working on. So I need something that will allow me to kind of move the microscope, or I need a better microscope. So at the moment it's not possible to see this in real time. And this sensor is also completely unprotected, so if any flux gets into the hole where the camera is, or where this light sensing diode is, then the sensor is going to be screwed. And I don't think it will be sensing anything after that. So one of them is on, and I'm going to solder the other one. Let's see, just so that I get the pin out right. The sensor has pin number 1 close to the bigger hole, and the sensor actually has let's see. The sensor actually has a number 1 pin marker at the bottom. So that's very practical, because the datasheet doesn't actually. The datasheet isn't very clear about the way that the picture where they show the pin out. So you could imagine that maybe the picture is either like flipped, or is it flipped, or is it like right side up, or so it's not possible to tell. But luckily there is a little marker which you can see on the picture, which shows where pin number 1 is. So based on that, I can easily align the sensor on the board and solder it. Okay, this one seems to be in place. They're a bit hard to solder, because you have to make sure that there is solder on all of the pads. I kind of tried the method where I would apply some solder paste along the pads, and then I would heat it up so that it would kind of form solder balls on the pads. And soldering after that was I got very good results. So I had all of the pads connected at once. But right now I didn't do that, so we'll see if it's connected. We'll see if we can actually read the version of all 4 sensors on this board now. And the code that reads it looks like this. So we have the this is when let's see here. This is when only 1 sensor was mounted. So let's see. Yeah, I should have all of them mounted now. And only range 1. It was only possible to read range 1 sensor. I should be able to read all of them. So once it cools down a little bit, I'm going to power on the board, and we'll see what the output will be. And this is the output of the console that's running on the stm32 F413 chip on this board. Alright, it's a moment of truth. Maybe something is shorted, maybe something goes up in flames, and all of that will be on the live stream. So let's get going. And let's see what happened. 2 of them work. 2 of them don't work. Why 2 of them don't work? Did I solder this correctly? So I connected the oh, I connect the, yeah. Okay. I connected the SDA line to the wrong pad on the other side. So the SDA and SCL were swapped. Let's get this fixed. Okay. So now SCL and SDA should be connected correctly on both sides. I'm going to bring up the console, I'm going to power the board on, and let's see, what do we see here? We see that range number 4, oh yeah, of course. So now that I have moved the sensors to the I2c 1 bus, I also need to update the device tree so that all of the sensors are on the same I2c bus. And doing this type of hardware hack right now, it wouldn't actually affect the software very much, because it will only involve a change to the device tree, the way that I've structured my code, so that all I will have to do is just reconnect things in the device tree, and all the rest of the code will just see the same 4 sensors, regardless of how they are connected on the hardware, which I think is a very nice approach to write embedded software. That I think device tree has really changed. It changed a lot of things in Linux, and I think it's a very good approach even for other types of projects, such as stm32 projects. You can easily include device tree in your project just by downloading the libfdt, and there is also the DTC compiler, and you can use the C preprocessor to pre-process your device tree before you actually compile it, in order to be able to use C macros in your device tree, which is very nice, very useful functionality. And in the true Unix way, it's kind of you kind of reuse the C preprocessor to do the job, and just let the device tree compiler take care of of compiling the actual integer values into the binary blob that is then loaded inside the firmware. So let's move the sensors from I2C. So actually I don't need I2C 2 anymore, but I'll still keep it there, because on the final board I will probably use I2C 2. But all I'll do is just rewire the 2 other sensors to I2C 1, and I'm gonna rebuild the firmware. Let's see. And when I type make with an exclamation mark in the command on the command prompt in Vim, it basically means that Vim shouldn't automatically jump to the first error, but instead just run the command and not mess with any of the buffers that I have open here in my layout. Which I think is quite practical, because I don't like when Vim automatically jumps to the first error. It can sometimes jump to the wrong thing, because if there is some command that you run as part of your build process that outputs something that looks similar to what GCC outputs, then it's kind of impossible to tell which one is actual error and which one is just something that some other tool has outputted. So sometimes Vim can actually jump to the first error, which is not actually the first error. It's just something that has been printed out in the std_out stream. So doing it this way still allows me to jump to things through this quick fix window, but doesn't mess with my buffers. Let's scroll to the bottom here, and it seems that we have all four sensors. Like, yeah, this is awesome. The next step here is to actually make a readout of the data, I think I'm gonna do this in the next video because I need to go to the toilet. I will actually do that, and then I'll come back and I'll continue with implementing the readout. Alright, let's see what we can do with this sensor. I'm gonna just check a few things here. The stream is still running, good. Everything seems to work. Still running, good. Yeah, oh, there's sound. By the way, Damien, do you think the sound is okay? Because I can't really play too much of the sound, because then it's going to just loop through the stream. But I think the sound is okay. Which model of ThinkPad do you mean? I have which model is this? It says in my terminal, it's L540. Signal 1 paste. Like when Arduino sold a paste or Flux or anything else online, you no longer ever know if it's genuine or not. It can be anything. Signal 1, let's see. It looks like intestines, I think. It looks gooey. But yeah, maybe I should try this. I'm definitely open to trying new products to make my job easier. Let's see. Yeah, this is not hot air. This is actually the fume extraction. So I'm going to turn it off. I have created a really nice. I'm very happy with this way of doing the fume extraction. I have a vacuum cleaner, which on the back of the vacuum cleaner there is actually a compartment where they put the filter. So I took one of these coal filters. That I got from China when I ordered one of these fume extraction things. I don't know if it's a genuine filter even, but it looks like a coal filter, and they advertise it as coal filter. And I put that filter in the back of this vacuum cleaner, so that it's the air actually goes through the bag of all the dust and shit in the vacuum cleaner.
So that kind of gets rid of some of the particles. And then there is this coal filter, and then the ordinary filter that is actually in there in the vacuum cleaner. And I find that this does a pretty decent job of cleaning, like sucking out all this smoke that comes up when I start soldering. I probably need to have it a little bit closer to my work area here. I moved things around, so I need to kind of make sure that everything is in the right place, closer together, so I get really nice airflow directly into this into the opening of the vacuum cleaner. And I need to put some net on the actual opening, so if some component decides that it wants to fly into the vacuum cleaner, I can just catch it. But I think this is a decent solution. Like I could order some fume extractor, sure, but like the most important thing, like the thing that actually does 95% of the job, is to actually getting this smoke out of where I'm breathing. So the important job is handled exactly the same way. Like I can't imagine some fume extractor doing this job better than the vacuum cleaner, unless it's a big fume extractor that maybe creates more airflow. But besides it's just the airflow. So the airflow needs to kind of catch all this air that is above the work area and suck it out. That's the main job of anything that's kind of like the hose that is located close to my work area. But then this the way it cleans, I don't really smell any. I don't smell any kind of solder residue. Even when I get out of my work area and come back, with like so that I'm not accustomed to the way it smells. I don't feel the smell of any solder, or any flux, or any this smell of the smoke. So I think for now this works really well. Maybe I will look into getting some like improving my work area, maybe having some fume extraction at the top here, or doing something else. But I think just having this is really good. Without this, I get smoke all over the place. I get it everywhere. Like I have to wear some kind of gas protection or something, because it's nasty smoke. I don't like to breathe the smoke, and I don't like to get any of the residue into my face. Because yeah, so cheap way to fix the fume extraction, just use a vacuum cleaner. Get some filter if you want to have an extra filter, and that's it. Does its job. Please wait. Suddenly I have power out, power cut. Well, you're welcome to come back. I'm not going to wait, but you can always watch the stream afterwards. Like it's all recorded, so I don't think you will be left out in any way. Let's see. So the next step for me is to actually look at this datasheet. Where is the datasheet? There. And there is actually another application node. So there is a few parameters that need to be set in the sensor during the startup, which have to be there is like an initialization sequence. You can find it in the code. Yeah, by the way, what do you mean by ALS module? What ALS module? Do you mean the sensor, or do you mean something else? Do clarify. Yeah, so there is an initialization sequence for the sensor. This is available in the Arduino library that reads this sensor. And it's also available in the application node. Let's see. Arduino library. License. Creative Commons share alike. Yep. Sounds good. And let's check the code for this initialization sequence.
So this is exactly the same code that they have in the datasheet, and this is actually even linking to this application note. This is kind of like, it's not readable, to say the least. But try to go over all of the registers and all of the values. That's a bit too much work for now. So I'm just going to copy this and paste this into my code. Let's see, VL. And let's do the initialization sequence. Let's make a method for it. So it's going to be static, and it's going to be an int because I want to make sure that I can return an error from it. And then it's going to be VL6180 upload or configure module. VL6180 itself, and then we have the code here. It goes like this, and then I'm going to do like this. Okay, cool. And next, I'm going to actually what I want to do here is I'm going to use the same way to check for the error. So let's see here. So check. Damn it! I should have done this as part of my replacement. I don't know it in my head how to, I would have to look it up, how to go to the beginning of text on next line. That would be kind of useful in this situation. There is probably a shortcut for doing that by combining some of the basic Vim commands. But I'm just going to use the pre-recorded dot macro. So everything I do, every operation that I do on the text is always recorded. The latest operation that I've done is always recorded into this macro that is accessible using the dot. So that's how I can get. That's how I can get Vim to do the same operation like this. So now I've entered the parenthesis, and I can just repeat the operation using the dot. So is this, let's see. Yeah, this looks good. So check, and then we're going to do like this. Check VL6180 configure module. And this will go after, let's see, after this initialization sequence. So VL begin, VL end. Let's do like this. So I'm gonna do VL end after this, and let's see if there's anything else I need to do. So system fresh out for Z. That's, let's see. Yeah, so this is what this procedure does as well. This will just check if it's fresh out of reset. 16. Okay. And I'm going to write this register according to the datasheet. I'm going to write a 0 to this register. So 0 and write red. Let's see here. So I don't have this GPIO connected to the microcontroller, which I probably should have done, but I don't have that right now. Let's see, averaging sample period. I could probably use a lot of similar settings, but I have to go over them and just use stuff that makes sense. Model, date, time. And also this part is important. So I'm going to set addresses from the device tree. I'm going to configure the addresses through the device tree, and then I don't need to do the begin and the end. So I don't need to restart. Actually, that's very important because if I restart the sensor, I'm not 100% sure if I toggle the enable pin and put the sensor into power down mode. I'm not entirely sure if the configuration is kept. If it is, then getting it out of power down mode and kind of continuing to use it is fine. But we would have problems like, for example, if I need to start a reading and then come back and read it out, then I cannot do anything on the bus while the reading is happening, because in order to access like other sensors, I would need to toggle the power pin. So I don't want to do that. So I'll set unique I2c addresses from the device tree, which sounds like a reasonable way to do it. And then I will configure each sensor to have a unique address. Let's see, read, yeah. Okay, pretty cool. Let's start with the configuration. Default settings. Let's see. So and this will actually be, let's see if this works. Delete to that. Yeah, but then I need to do the insert. Yeah. So let's like this. VL6180 as X set register replace this with check. Check VL6180 right reg and self and comma. Okay. I need to play more. What's it called? What's it called? Vim Explorer. Vim game. The Vim game. It was a really nice game. It was many years ago I played it. Many years ago. I don't think it was many years ago. It was a few years ago. It's called Vim. What's it called? The Vim game. Vim Adventures. Yay! The Vim Adventures. It's a really nice game. Like this is the perfect game to learn Vim. You start from the basics and then you learn as you go, and it's actually a game. It's actually a fun game. Like when you have to jump from one point to the next, like you have to figure out how to do that using Vim shortcuts. This is perfect. I need to play this again. Let's see. So, what's up with this one? Oh, this one actually didn't replace correctly. Early convergence estimate. Yeah, it would kind of make sense to have a separate method actually for the 16-bit. So VL6180 write reg 16, and let's see. So let's see if there is a registers definition somewhere here. Okay. Pretty good. And I never use Arduino code as is, and there is a very good reason for that, and I'll show you in just a bit. Because it always needs to be revised in some way. Let's see. First I'm gonna add these, and let's see. Make the names shorter. System. Okay. And next is sysrange. Sysrange. This one is not going to be shorter. Which one is next? sys ILS and result. Yep. Let's see. And anything else just ends up being reg. So 21x, and let's replace this with reg. Okay. Looking good. So now all of this code should be correct as well. So read out averaging sample period. What is that? Let's go over all the registers and just make sure that everything makes sense. And also just check what capabilities the sensor has. So, Damien, which answers did you miss? Which answers didn't you hear? I'm not sure when your power went, so I was curious though what you meant by the ALS module. By the way, everyone, if you're watching this, this is a live stream. You can take part in the live chat, or you can subscribe to my channel and you can watch my live streams live, because you're going to be notified when I start broadcasting live. And then you can take part in the live stream. And you can also join Discord. There is a link in the description down below. And you can leave me a donation. You can donate some money if you like my work. So that's always appreciated. Next, I want to just find this system. Let's see. Range. Average and sample period. So it's set to 30. So this is actually default. Like, why even do that? This is useless. Firmware. What does this actually do? Read out average and sample period can be adjusted from 0 to 255. Decreases noise, but also reduces the effective max convergence time. So it decreases noise and reduces the convergence time. Right, okay. So it seems that the sensor is probably going to take several, so this would be the sample period. So if we increase the sample period, then it can sample for a longer period of time, which decreases noise and reduces the convergence time because each sample will have more data. But it will increase the power consumption because the LED has to be on for a longer period of time, which is not a problem in this case. So we could actually set it to, we could actually try to set it to 255, but I'm not going to do that just yet. I want to try this setup first, just to make sure that everything is working. I'm going to set this to 255 and comment it out. Analog gain. Sys ILS analog gain. This is probably useful. This could be useful for measuring the ambient light depending on the lighting conditions. Like if there is a lot of light, then we don't need much gain. If there is very little light, then we need a lot of gain. So this is set to 46, which is not the default. 40. What? This is ALS analog gate. It's set to 46, so this is obviously wrong. This is why I don't like using the Arduino libraries as is, because they are not always correct, and they're not written with real-time RTOS in mind. So any kind of delays in the libraries, I would replace them with the proper delays. And where possible, like if there is a delay that is, let's say, 800 microseconds, and it doesn't have to be exactly 800 microseconds, then it's better to make it a millisecond delay, because then the task can actually sleep and not, and kind of everything else can run while the task is waiting, instead of the task wasting CPU cycles. In terms of precise microsecond delays, I use the DVT counter. This is the debug macrocell counter, which counts clock cycles. So it's actually possible to have a very precise delay function that measures by clock cycles. But that, on the other hand, also puts the CPU under 100% CPU usage. So anything, if there is a task that is gonna, like, you also kind of, to get this perfect microsecond delay, you have to disable the scheduler. Because otherwise you can have your task swapped out while it's in the middle of delay, and then the whole point of actually having a precise microsecond delay completely disappears. So I don't use sub-millisecond delays very much, precisely because of these implications. Let's see the next register here. Is sysrange VHV. Repeat rate. What is that? So this is some kind of something related to the auto operation. And this is for some reason set to 255. Auto calibration period. So it's quite possible that this auto calibration period, should be performed when the sensor is actually pointing at something. So doing it right away probably doesn't make any sense. Sysals integration period. This is right. So this is for the. Is this for the distance, or is this for just the ambient light? Yeah, I think the ALS, is the ambient light part, and the range is the ranging system. So sys ALS is the ambient stuff. Single shot. Okay. So I'm at the moment not interested in the ALS. I'm gonna set it to default. And this actually performs the recalibration. So this is something that needs to be done explicitly, perhaps on command from the CAN bus. Let's see, intermittent period. intermeasurement period. This is also for the ALS system. Interrupt new sample ready. This is not necessary because I don't have that connected. And this link will go up here to provide a reference for this magic number block. What else is here? So I need it to operate much faster. I don't want to have 100 milliseconds period between the ranging. Actually, it's probably a good idea to just comment all of them. And see what we get. Okay. Next, I will check the source file again. Yeah, so next is the address change. The address, let's see, I don't have anything on the I2c buses, so besides the sensors. So I could set the addresses to actually, yeah, they have to be set with this most significant bit set to 1, because that is not, or is it programmable? Is it programmable actually? No, actually, I think it's programmable. I think the whole address is programmable. Let's see, address. What was this address register called? Slave device address. Slave device address. Yeah, so this is a 7-bit address, so this can be set to anything. So let's configure them as yeah. So I use the reg property for address, and I'm gonna just set them to 80, 81, yeah, etc. So like this, depending on the number of the sensor. 83 and 82. Actually, I'm even going to number it like this, starting from 1, so that everything corresponds to the correct number. And then I'm going to read the reg property here. I will get it from the FDT. So uint8 FDT get int or default FDT, and the FDT node of this particular driver instance, and reg and the default value. Okay. Now it's important here to actually do this after we do the initialization of the let's see. No, actually, after we do this. So first, I want to make sure that the device is of correct model, and then after that, I will set the address. So first, it's going to be default address. We do begin. And then we do Yeah, and let's actually move this code up here. So I'm gonna store it in a local variable because I still need to set this address. So int 8 new addr, and the address set to default for initialization, and then over here, before I do the configuration, I'll do check VL6180 write reg self VL6180 i2c reg i2c slave address, and this will be set to new addr, and then self address will be updated to new addr. Or actually, this will be updated. This will be updated by reading the register, which is a safer way of doing it. Read reg. And then we check if the addresses match. Self address not equals new address, and then print k, print error, VL6180 could not set device address. Return -1. And at the moment, this will always fail because I made a huge mistake when assigning the addresses, because these are let's see, yeah, because this will be shifted, so they need to be can make this 4. Let's make this 4. These ones will be shifted by 1 to the left when writing to the device, so they will never match otherwise. And by the way, so this would be the 7-bit address. So I assume that this register should contain the address shifted to the right. Yeah, it looks reasonable. So the actual address sent on the I2c bus is going to be shifted to the left, which is already handled by the I2c driver. And the value stored in here is going to be the raw address of the device without the read-write bit, the least significant bit of the I2c address. Okay, so I set the address, and what else do I need to do? Let's check. What should I return here? Like invalid? Let's see. No, I can't jump to that. Let's see. No dev could be a reasonable return value. Too many open files. I think no dev sounds like a good return value here on not identifying the right model. So I'm also going to add the function for reading, for making the range sensing. But I'm going to check first in the source code what else I could be missing. So I'm going to leave the ambient light for a bit later. First I'm going to get the ranging working. Get register, and yeah, also the 16-bit stuff. So set register 16-bit basically just writes. Yeah, so data, yeah, okay. I'll add two more functions here. Read, actually I also need to add the write reg. Let's put this write reg. Or let's make this read reg 16. So transmission buffer is the register address, and the reception buffer should actually be, in this case, yeah, should be a local variable. And then I'll read two values. Actually, this should be uint8 rx with two fields. And then I should just convert that to uint16. This will compile correctly when it's done like this. Let's initialize this to 0, and r, return r, and then if r more or equals 0, then then I'll just do value equals yeah, it will get data high bits first. So this 8 points, and or this with rx1, and then all of this will be converted to uint16. And this will be write reg, uint8 value, and value like that, tx 3, and then i2c transfer tx 3, and null 0. Okay, and the same thing for the 16-bit. I have to do the explicit casts because I have the warning options enabled in GCC, which disallow non-explicit casts in this situation. So it would complain otherwise that I'm trying to convert 16-bit value into 8-bit value without any explicit cast, which in this case is fine. but in a different situation, it could actually be a problem if I would do that and not get warned about it. So by default, like if you don't use any warning options in C, C will allow you to do pretty much anything. Like you can even write code that doesn't make any sense, that will not work, just by definition. Like because of things like costs and value conversions. But it looks like correct code, but it will not compile properly, and GCC will not actually tell you that it's incorrect. It will not complain at all. And then you get all frustrated why the C code is not working when you're not using any warning flags from GCC. So what I do is I set as many warning flags as possible. Some of them are prone to generating a lot of false positives, but I try to set as many as possible without kind of making my life harder. And then I also enable all warnings to be errors. So if there's any warning, then it's automatically converted to an error, and the program stops compiling. And I think that's a very good way to configure the build environment for C. Okay, so moving on to, I'm gonna add the read method here. I'm gonna make this into, I'm gonna make this this driver export an analog interface for each instance of this driver. So it's gonna be like this. I will add an analog device here. And then we can have channel 1 as range and channel 2 as ambient light. This will, yeah, actually analog is already included, so I don't need to include it again. All I need to do now is initialize the analog ops. Static const struct analog ops, analog device ops. VL6180 analog ops, read analog read, write equals analog. Let's call this VL6180. Prefix it like that. Right, and next. This is going to be static int VL6180 analog read, and it will get the analog device as argument, and it's going to get int 32, I think, as channel, and then float value. The same thing for write. Except in this case it doesn't make any sense to write anything. At least not yet. So analog read, analog write, and the read method is going to do, let's see, so I need to also initialize this mutex. So thread mutex init self block. Initialization can go on without blocking the mutex. There is really not much else besides taking a measurement that needs to be exclusive. So So range is actually 0 to 255 then. Start single shot. And this delay, let's see, Arduino delay. Is this milliseconds or microseconds? Probably it's milliseconds. Yeah, milliseconds. Let's see how much we need to actually wait according to the datasheet. So single shot mode, single shot, range, single shot. Okay, so this can actually also maintain a history on the chip. Recommended readout is 4.3 milliseconds. Okay, let's see. So setting it to 48, what does that actually mean? How many milliseconds is that? So there's 3.2 milliseconds pre-calibration. Convergence time up to 63 milliseconds. Let's see. Default is 31, range timing, let's see, range timing, so this will be 31 milliseconds and then readout 4.3. Okay, so this will need to be configured based on actual performance of the sensor. Range error codes, also something I need to read. Let's see. So why is this waiting for 10 milliseconds? this is supposed to wait for 4 milliseconds plus, let's see, 4 milliseconds plus 31 plus 5. So around 40 milliseconds. Okay, based on this I should at least get some reading. So I'm gonna go to my main application and I'm actually gonna read out the sensor and draw the result. Let's see. Okay, I'm going to add the pointers to the devices. Analog device range 1 and 2, 3, 4, and then in the input I will also add range inputs, and let's see. So actually it's going to be even to 8. And it doesn't make any sense to make this into an array because we're still going to have to use the values individually for, let's see, 1, 2, 3, 4. And then there is going to be another function that will convert these values to an actual reading. Or actually, no. This is going to be a direct measurement. This is going to go directly into measurements. Or actually, I'm gonna save them here, but I'm gonna save them as floats because I want to keep all of the interaction with devices in one function and any calculations in another, so that I don't interact with devices randomly in code. Because every interaction with a device connected to the chip is potentially a long time operation. So I want to keep track of all the operations that can potentially take a long time in case they eventually time out, and to kind of keep them in one place, so that if I need to add any monitoring for that, I can easily do that later. So for float. Let's see, no. Float. this, and maybe I will need to update the interface to the analog device. We'll see. Let's see, input, so read range, and then 2, 3, 4. And in fact, because I don't need to do any conversion, I will just do like this. Let's see. What should I call this? So like range sensor, channel range. Range sensor channel range, and then there's going to be range sensor channel ambient. And this will be analog read. So this will plug into the analog interface of this driver. Right, and also so because it takes time to read the sensors, like this will have a convergence time of 31 milliseconds. Eventually, I would want to break this out into a separate thread. So the way I use threading is to separate time domains. So when I have something that ultimately belongs in two different time domains, like one loop that runs at 1000 hertz, and maybe some other piece of code that cannot execute at 1000 hertz, like this one, for example, then I find that it makes sense to separate that into two different tasks. So that one task is running in the time domain of the high-speed loop, and another task is running in a slower loop, but it can still be sort of like it can have all the functions in a sequence, but in between there it's going to sleep for long periods of time until it gets the data that it requested from the device. That's what happens here. So this function will go here, and then it will sleep for this period, waiting for the return. And I will also need to check here in a loop probably whether the return has actually whether there is a reading in the sensor which is valid. For now, I just want to test this as quickly as possible. So I will just compile the code, and once I get some readings out of it, I will add more code here to test whether the reading is actually ready. So let's see, inputs range, and then I will have a function called UI, which will draw this indicator, let's see, X, Y, 11, let's see, 11, 12, 13, 14. Let's put this at 2, 14. Range number 1. And 2, 3, 4. 2, 3, 4. 14, let's see, 14, 15, 17, 20, and 23. This is the XY positions of the indicators in the UI. Let's see what we get. Redefined. Of course, it's redefined because I forgot to remove this. This will go away and recompile. And then we have access elements. 4. I wouldn't be surprised that if you don't enable the flags, it will probably not even warn about this. Like it will just assign the elements that are in the list and just discard the other one, or do something else that's undefined. Let's see. Fresh out of reset. Where is that? Okay. Reg sys fresh out reset. And then in the check here, I will actually return the error IO for the communication error. Let's see. Okay, now there is a lot of errors that that stem from the previous error, so I'm going to recompile and go again. So reg sys range self is undeclared. Struct self VL6180 self is container of dev struct VL6180 dev ops, because this dev will point to the analog device, and also I need to register the analog device. So I'm going to initialize the analog device here. Analog device init self dev f2t node and VL6180 analog ops, and then register the analog device. Register self dev, and now this will make the device available to the other drivers in the system. So uint32, so this will need to be uint32. And system interrupt clear. Reg system is not supposed to be reg system, it's supposed to be reg sys. And this is obviously analog write. Result range valve. After a few arguments. That's what it was. And now this will need to be converted from and this will need to be logged for the full duration of the reading. So if multiple processes want to take a range readings, which usually is not going to be the case, but if multiple processes want to read this sensor at the same time, it shouldn't be the result shouldn't be that one process starts to kind of writes this start measurement of the range, and then a different process arrives and does the same thing. The second process should wait on this lock, so it will actually be swapped out from the CPU. It's gonna be put to sleep. It's never gonna run until the lock is unlocked, at which point the second process is gonna run and take the measurement. So I'm gonna unlock it here and return R, and I'll update the value. So value equals, so what is the range result? Result range val. So where is this register? So let's see. What's it called? Like, there should be a register called result range. Let's see, range val. Is there a register called range val? Result range val. Okay, it's actually 2 underscores there. That's why I didn't find it the first time. Final result unit is in millimeters. So yeah, which is actually perfect. I didn't have to make this a float, but I'll just convert this now to directly to millimeters. So actually, I'll return float val. Let's see. Okay. Compiling this, and let's see if there's anything else that needs to be fixed. So makes pointer, yeah. Okay. So in my interface, I defined this actually as I think it was just this part that was different. Unsigned int instead of uint32. Let's see if that compiles. Yeah. And VL6180 analog write. Yeah. So uint32 and unsigned int are 2 different types, because uint, even though they may be the same type in the system here, they're still uint32 is still type deft separately. So compiler, as far as compiler is concerned, they're 2 different types, which is good that I get a warning there instead of just a blind conversion between whatever value this function accepts, like between the prototype of this function and the prototype of the pointer which I assign to point to this function. Very good that it outputs a warning for that. So analog write fixed, and let's see, date high and date low. Let's see, module date. Yeah, and actually this can be read as a 16-bit value. Drag 16 and time. It's always a good idea to always initialize the variables that are allocated on the stack, because otherwise you can have undefined behavior. If for any reason this function is not going to set the variable, then the variable could potentially have any value, unless it is initialized. And the final thing here is the return from this function, return 0. And I think I will need to, did I configure all of the device tree variables? Let's see. I think it was only the address I had to configure. Yeah. At least for now it is only the address. That would be the default channel 0. Actually, I'll also check here if the channel is 0 or 1. So if channel equals 0, then we do the readout like this, and else return invalid argument. And the indicators will be floats. Let's see. Okay, it's the moment of truth, and no sensor works. Yeah. Only one of them works. I think this is related to the address. Somehow, yeah. I think it's both related to the address and the fact that I didn't disable this. Let's see. There is this GPIO 0 pin, which enables the chip. So I shouldn't be doing this. I shouldn't be doing and there. I should just enable the chip. And let's see. Let's also print out which address it is actually using. And then after that, I check for configure module. So this should work. But even this part actually failed. So this tells me that maybe maybe it doesn't actually set the new address properly. Or maybe the new address is actually not even read from the device tree. Let's see what it. Let's. Maybe it will even. Let's see. Actually, it fails from here, and this explains why it. Yeah. This needs to be. Let's see. No, this should actually not fail, because this just reads the register from. It actually needs to read the register from the new address, though. That's true. So this is a bad thing to do. We don't need to do that. I just write the address and just set the self address equals new address after writing the right address, like this. Let's see if this works better. Okay, at least number 1 works. Number 2 doesn't work. So for some reason, if the chip is not disabled, or like put to sleep, so maybe I need to do begin and end here. Let's see if that actually works. So configure module and then end like this, and then also begin and end here. Let's see if this works. This should not be necessary, though. It seems very strange that this will be necessary, because they are supposed to be configurable. I think what is actually happening is probably that all of them are actually on by default. Let's see here. Let's check the defaults. Yeah. So I set all of them to on, which was part of testing when I was debugging this board, and I couldn't communicate with them at all. So I set all of them to on, which essentially makes all of them accept the new I2c address. So it's impossible to communicate with the other devices after that. It's important to initialize the GPIO pins to be low while configuring each device one at a time. And then once the device is configured, then they can all be on at the same time, once all of them are configured one by one. Or actually, as soon as the previous one has a new address, so that it won't accept commands going to the default address. Then it can be left on while talking to the other sensors. But at startup, they should all be off. Yep. So this is much better. There's still a problem with range number 3, though. I wonder what the problem is. What is wrong with range number 3? Right, the problem is that, could it be that, let's power off the board and see if this works. it still doesn't work. So so why not range 3? Let's actually remove this end there, because I think it's quite possible that the sensor, yeah, so actually the first begin should be there, not the end. Let's see. Something's wrong with range 3. Time to debug. The stream seems to be alive, at least. So I'm gonna measure with my scope and see if there is anything unusual happening on range 3. Range 3 is going to be connected to pin 0. Let's have a look here. It's going to be also range 3 here. And this one is at the top there. Okay. I think, could it be that the diode is actually mounted back to front there? Yeah, I think
think so. I'm gonna. I think I soldered the diode with the cathode where the anode should have been. So I'm gonna just rotate the diode and we'll see if that works. This diode is not strictly necessary now that I'm using 3.3 volts on the I/O pins, but I still put back all the diodes that I removed before, or at least most of them. I'm gonna put back all of them and just leave them there, because it seems to work fine as long as they are mounted with the correct polarity. But they're not necessary anymore. The purpose of this diode originally was to allow pulling this line low when this one is pulled up to 2.5 volts. So you don't want to kind of have the possibility of the microprocessor pin to drive this line with any voltage, because this is going to be 3.3 volts. So a diode is a good way to handle the situation where you just want to pull this low. So you can pull it high behind the diode, and then use the diode to lead the current to ground when the microcontroller pulls this line low. But in this case, I instead use the. Actually, I could make this into open drain pins, in which case it doesn't really matter. Only matters if it's push-pull. But still, the resistor is quite big, so even if there would be current flowing through this 3.3 volts going through this resistor, it's still unlikely, but it will probably increase the voltage a little bit. But it's going to be very small current flowing there. So let's see if this works. Okay, so now instead I have to check all the diodes, because it could very well be the case. Let's see. So if now the pins are set to open drain, they should still though be set to zeros. Interesting. Let's revert to push-pull and see if this works better. Chances are it's going to be the same result. I'm pretty sure it's going to be the same result, but I could be wrong. And that's okay. I'm going to continue trying different methods until I get it all right. So the diode is some of the diodes actually have this flux on them, so it's pretty hard to see where the anode and cathode is. Oh, right. Well, this explains everything. One of the I actually did not put on the diode that corresponds to this the sensor that did not work, because it is actually the, let's see, yeah, because the board is flipped around, it is actually the sensor that is on the left side instead of the one on the right side. So I was looking at the one on the right side, and that one didn't have a problem.
But on the other hand, the diode that I moved seems to have had the correct orientation from the beginning. It didn't have the incorrect orientation. It's just that the silk screen is quite close to the pads of the diode, so I mistakenly thought that it had incorrect orientation. But the diode that will fix this is going to go to the chip that did not get the correct signal. Let's see. So this one goes here. I think this goes like this. Let's see if it works now. Let's see if all of the chips now get their chip select signal delivered to them correctly. The board is not really hot because, yeah, now it's working. But range 1 is missing, and I wonder why. That's probably something to do with how I define it here. Let's see. Range 1 is missing because... yeah, because I didn't reference them here. Let's see, range 1 equals range 1. And this will just make sure that the application gets the references to the range sensors. Like this. Reference, and also of course the nodes need to have references attached to them. So this will be range 1. Range 3. And they are in this order here because I was testing them one at a time. I had to do the test with a while loop, where I would constantly try to communicate with the device while I could measure it with the scope. So actually I can put them back in the correct order now. Okay. Let's see. The device tree compiles. And we are running. And let's see if we can read them. 255. Yeah, look at that. Range 1 is not working though. There's something wrong with range 1. But let's see how exact they are. So I'm gonna take I'm gonna grab a ruler if I can find one, and I'm gonna see how exact the sensors are. Let's try this one. Now I have my finger at around 5 centimeters. So it should read about 50. Let's see. It reads 60. Is this the correct one? Yeah, this seems to be the correct one. Maybe I could use something else other than my finger. Maybe I could use a piece of paper or maybe my tweezers. Let's try with the tweezers. This is a reflective surface. So let's see. Place it at 40 millimeters. It reads 49. If I place it at 60 millimeters, then it reads 60. Interesting. If I place it at 10 millimeters, it reads 20. So there is a bit of discrepancy in the way, and there is quite a lot of variation as well. So I'm holding the tweezers pretty still here. And it goes anywhere between 15 and 20. But at a larger distance, I think it's going to be a bit better. So this is 35. Let's see how much it actually is. It's actually 25. But then going to, let's say, 70. Let's see, is it? No? No? Like, seriously? Is that my terminal, or is that something else? Let's see. Yeah, that's the terminal. I'm going to restart the terminal. Let's try 70 again. So I'm gonna place the tweezers at 70 millimeters. Yeah, I'd say it still varies a lot, but it's a bit more exact, more closer to 70. Actually, now it's closer to 80. So there seems to be this error of 10. I'd have to check the datasheet. Maybe there is some setting for this. But the one that's not working, which one is that? I think that's maybe that one. So why is this actually even returning anything? It's not supposed to return anything. It's this one that's not working. So this one works. Oh, this one is actually. This one is it. I think this one is actually better. Measuring. Let's see. Is this 10 millimeters? So this is 10 millimeters. Yeah, this one is a bit better. I wonder if there is some dust or flux or something else that maybe got into the hole of the sensor that is causing some sensors to malfunction completely, even though communication is okay, and some of them give wrong readings. So it could be anything. The sensor, the hole where the light sensing element is, it's completely open, so anything can get in there. Which is a bit unfortunate. Like, even the flux will easily get in there. And the datasheet says that the manufacturing process should be a no-wash manufacturing process. And I washed all of these cards in isopropanol. So, I don't know. Maybe it's something like that. I could try replacing the sensor and seeing if a different sensor works. If that works, then it's probably something to do with the sensor perhaps being clogged or something like that. All right. So that's it for this video, and until next time. Let's see. Stop the stream.